Alright, so we're going to look at the idea here of an inverse. Now, you've probably used the word inverse a lot in English or just, in everyday conversation, but in math what it means is you're reversing or quote-unquote undoing an original relation or function by doing everything in the opposite. So the opposite direction, so the opposite order I should say, and the opposite operation. So to use sort of like a real-life example, picture an example of somebody's morning routine. Okay, and I know yours obviously might be a little bit different. Hopefully you guys have a breakfast and toothbrushing somewhere in there. But just for a simplified version, let's take a look at this. So let's say you start with waking up, followed by taking off your pajamas, then getting dressed, then putting on your shoes, and then leaving. Okay, and just think about what that would be if you're going to do the inverse. So you'd be undoing everything you just did, but of course in the reverse order in which you did them in the first place. Okay, so if you're coming back and doing the opposite of leaving, well, that would just be returning home. So I'll just say return. Okay, well, okay, so then you, instead of putting on your shoes, you're going to remove your shoes. Okay, instead of getting dressed, you're going to undress. Instead of taking off your pajamas, you're going to put on your pajamas. Then, of course, instead of waking up, you're going to be going to sleep. Okay, so again, this is just an idea of the inverse. You'll notice that we reversed all the operations or the actions, and of course we reverse the order of them as well. Okay, so we're going to be applying this to some actual relations and functions and seeing what that means in terms of graphs and everything else. So you've actually have used an inverse before in math. We didn't necessarily call it inverse as much in grade 10, but when you had a problem like sine x equals 0.5, so you knew the ratio, the sine ratio was 0.5, you need to figure out what angle created that ratio, we did something called a sine inverse. You remember it was above the sine button in your calculator, had the little -1 for notation in there. So what that operation, that sine -1, is called the sine inverse. So it undid the sine ratio to tell you what the original function was, what the original angle was. So that -1 is notation that's used very, very commonly for inverse, and it's written as an exponent. So if you had a function f of x, the inverse would be written as f with a little exponent of -1 of x. Now, it can be a little bit confusing because if you did any negative exponents last year in grade 10, you might remember that, let's say you have x to the -1, that means the same thing as 1 over x. Now, it's not technically the same thing. It's written as an exponent, but it's not technically an exponent. The notation can get a little bit confusing, but just note when you see something like this, it's referring to the inverse and not actually meaning the same thing as 1 over the original function. Okay, that's the reciprocal, not the inverse. Okay, so it's not the same thing. So hopefully, that sounds a bit confusing right now, but you'll see once we go through some examples that the notation is pretty common. Okay, so let's take a look at an example here. So let's start with a relatively straightforward line that we've seen lots of back in grade 9. Okay, and so we have y equals 3x minus 7, okay, and we know the equation of that is just simply going to be simply that, y equals 3x minus 7, or in function notation we would have f of x equals 3x minus 7. Okay. What I'd like us to do is sort of build this equation using an input-output diagram. So what that means is that I'm going to start with x in my equation, and I think, okay, to build this equation, build this relation, what's the first thing that happens to x? Well, if I look at x, the first thing that happens to it is it gets multiplied by 3. So I start with x, and I multiply by 3. Think of this as like your morning routine, right? You're starting with x, and you might, wake up, and then you might, take off your PJs. Well, we're starting with x, and we're multiplying by 3. Once we multiplied by 3, you'll see we then subtract 7. Okay, and that gives us y. So to get the inverse of this, what I'm going to do is, again, do the complete opposite of all these operations and do them in the reverse order. So going backwards, instead of subtracting 7, I'm going to do the opposite, which is going to be adding 7. Okay, and then next, instead of multiplying by 3, I'm going to divide by 3. So what does that mean for an equation? Well, I'm going to have x, and I'm going to add 7, then I'm going to divide by 3, so this whole thing is divided by 3, and that is equal to y. So this right here is going to be the equation of my inverse. Okay. Or if I want to put it in function notation, it'll simply look like f inverse, see that little exponent of -1 as a notation, f inverse of x will be x plus 7 all over 3. Okay, so this is a nice way of finding the inverse function simply by doing an input-output diagram to create the function or relation, and then reversing the order and the operations to get the inverse function. Okay, so again, there are other ways of doing it, which I'll show you, but this is one approach of doing it, which tends to work quite well. Okay, so there's some other stuff I'm going to have you do here. So there's a table of values down here. I just want you to create for this line. So when x equals 2, if I put into the function here, I get 3 times 2, which is 6, minus 7, which is negative 1. Okay, when x equals 4, 3 times 4 is 12, minus 7 is 5. And if I repeat the process here, I'm going to get a certain number of points here. Now, I want us to then go and look at the inverse function over here and see what happens when I put in negative 1. So if I put negative 1 into here for x, I get negative 1 plus 7, which is 6, divided by 3, which is 2. And all of a sudden, you might see a little bit of a pattern here. On the original function, when x equals 2, y equals negative 1. Well, on the inverse, when x equals negative 1, y equals 2. And what you're seeing here, hopefully, is that the x and y values from the function to its inverse are simply interchanged. So that means that when x equals 5, I should get, if this pattern is holding, that y is equal to 4. So let's try that. 5 plus 7 is 12 divided by 3, and it's indeed going to be 4. So without doing too much more other work, I can already tell 2 other points. I know that when x equals 11, y will be equal to 6, and when x equals 17, y is equal to 8. Okay, so again, what you're seeing is all the x and y values of each point are being interchanged with each other. Okay, so just to summarize here, f of 2 equals negative 1, which means the point 2, negative 1 is on the function. But when you put negative 1 into the inverse, you get 2, which means negative 1, 2 is an element of the inverse. So what this means to summarize here, that if you have a point, we'll call it AB, that's on the function, the point BA will be on the inverse, and vice versa. Okay, so a lot went on there, but that gives you an idea of how the function and its inverse are related, at least in terms of different points on the function and the inverse, and how to create the equation of the inverse from the original function using those input-output diagrams. Okay, so some other stuff with the inverse here. Let's take a look at the graphs of both the original and the inverse. So I'll put a nicer graph on Desmos here, just so we can see it. Okay, so there you see it, and it might not look very, very exciting. You see they intersect at a certain spot right here, but what might make this a bit more interesting is if I start putting the line y equals x on here, and let me just change the color on that just so it stands out a bit more. All of a sudden, you might see a bit of a pattern here that almost looks like they're mirror images of each other on the other side of this line. And that's going to be it's going to be the case with any function and its inverse. So if you take a look at the function and reflect it across this line y equals x, you're going to get the inverse, and vice versa. Okay, so keep that in mind, that the inverse is always going to be a reflection of the original in the line y equals x. Okay, so if you want to see a couple more examples here, here's another equation, y equals 2x plus 5 and its inverse, and there's a line y equals x in green. And again, here's the case of the parabola, y equals x squared minus 5, and the inverse is sideways parabola. Again, they're all reflections across the line y equals x. Okay, so what we're going to do here now is actually go through some examples of trying to determine the inverse. And that input-output diagram I showed you a couple slides ago will come in handy. I'll show you another way of going through it as well. But let's go through the first one together. So in this case, the function is actually just 3 points. Okay, so I have negative 6, 12, 5, 17, and 9, 12. So to find the inverse, remember that the x and y values from a function to its inverse are simply interchanged. So my inverse is going to be comprised of the points 12, negative 6. Again, just interchanging the x and y values. 17, 5, and 12, 9. Okay, so right away I have the inverse. And you'll notice here the inverse is not a function in this case. Okay, so the original is a function, but you see on the inverse that when x equals 12, we have 2 different y values. The inverse is not a function, which is true. It doesn't always have to be the case that the inverse of a function is a function. If you want to go back to this slide right here, you can see that with this parabola, x squared minus 5 is a function, passes the vertical line test. When you take a look at the inverse, it's now a sideways parabola, which very easily fails that vertical line test. So the inverse of a function is not necessarily going to be a function. Okay, now as for b, so let's rewrite this as y equals 1 over 3x minus 5. Okay, and what I want to do is I want to try and do the input-output approach to try and find this inverse. So just to remind ourselves of how it works, I'm going to start with x. Then I'm going to think, okay, what's the first thing that happens to x when I'm trying to build this function? So it gets multiplied by a third, or if you find it easier to write it this way because you don't like fractions, it gets divided by 3. So x gets divided by 3, and then we subtract 5, and that is going to give us y. So for our inverse, reverse the order, reverse the operation. So instead of subtracting 5, we're going to first add 5 to x. Okay, and then instead of dividing by 3, we're going to multiply by 3, and that should give us y. So how are we going to do that? So y is going to be equal to, I'm going to take x, add 5, and then multiply by 3. Okay, so that's going to simplify into 3x plus 15. And that's going to be the equation of my inverse. So the inverse is a function, it's just a line. So I'll write this as f inverse of x equals 3x plus 15. Okay, and if you like this method, this will work most of the time. I'll talk about when it doesn't work in a second. But I'm going to show you another way of getting the inverse as well, just in case you like seeing a different method. So the other way you can do this is we can start with our original function here. And let's make a copy of it there. And remember that we saw when we were looking at the points is that on the inverse, the x and y values are interchanged. Well, we can do that algebraically as well. We can take the x value, the x variable, interchange it with the y variable, and that will help me solve for the inverse. So that means I'm going to have x equals 1 over 3 y minus 5, because again I've interchanged x and y variables. Now technically this is the equation of the inverse, however it's not really useful to me unless I have y isolated. So what I would have to do next then is just solve for y. So how am I going to isolate for y here? Well, the first thing I'm going to do is add 5 to both sides. So that gives me x plus 5 equals 1 over 3y. Okay, and then I'm going to just simply multiply everything by 3. So now 3 times x plus 5 is equal to y, or y equals 3x plus 15. So see, you get the exact same answer in the end. And you'll even notice the operations I did were exactly the same too, right? I added 5, just like I did here, and then I multiplied by 3, which I did right here. So it's just a different, it's a more algebraic way instead of using the input-output diagrams. Both of them work. The only time that you might run into problems using the input-output diagram approach is if there's more than one x in the equation. So we're going to get to some examples like that, if not this lesson, then in a later lesson in the unit. But for now, as long as you only see one x in the equation, the input-output approach will work. Okay, so now looking at C down here, it's very similar to B. I'd like you to try this on your own. So you can use whatever method you like. You can use the input-output diagram, you can use the algebraic way of interchanging x and y, then isolating for y. And whichever one you prefer, go through it and try and find the equation of the inverse and push play and ready to go through it together. Alright, so let's take time to quickly check our answers here. So I did it both ways, so whichever way method you did, you can check your answer. If you did input-output, remember you're starting with x, then building the rest of the equation from there. So x gets multiplied by -3 first, and that's what gives you the negative 3x. Then 7 gets added to it, then you divide by 11, that gives you y. So again, reverse the order, reverse the operations for the inverse. So instead of dividing by 11, we multiply by 11, then we subtract 7, then we divide by -3, and that will give us our inverse. The inverse is still a line, so it's a function, so we use function notation there. For the second way, again, all we're doing is interchanging the x and y variables, so we get something like this, and then we isolate for y. And again, it's the exact same algebraic steps we did using input-output, but again, it's written a bit more algebraically. So either one is correct, and you should wind up with the exact same answer in the end. Okay, so I'd like you to try a couple more before we move on. So I'd like you to try C, so g of x equals 2x squared plus 3. And then I want you to try D, 1 over 7 square root of x minus 3 plus 8. And once you've tried them, we'll see you in part 2 of the lesson, and we'll go through them together.